Hello everyone, welcome to our lecture on hypothesis testing. Hypothesis testing is a cornerstone of statistical analysis. In this lecture, we will explore how to make decisions about population parameters using sample data. So we will cover hypotheses, p-values, significance levels, and z-tests with several practical examples and coding in Python. So let's dive in. So far, we discussed point estimation and confidence interval for inference of an unknown population mean. Today, we want to study a new methodology called hypothesis testing. In this lecture, we are focusing on four key concepts: hypothesis, p-values, significance levels, and z-tests. By the end of this lecture, you will understand how to set up hypotheses, what are the p-values, how to choose significance levels, and how to perform z-tests to draw conclusions from data. First, let's start with hypothesis. The terminology hypothesis means assumption, presumption, or guess, or you can say a proposed explanation for phenomena. A hypothesis is an assumption made before any research has been done. For example, if early morning your vehicle does not start, the observation is the car won't start. The question is the battery dead? The hypothesis for this case is, if the battery is dead, the jumper cables will help it to charge, and the car will start. You made an experiment here. You hook jumper cables up to the battery, and the result is the car starts. And here you can make a conclusion. Your battery was dead, and your hypothesis was correct. Then, based on this experiment, we may conclude a theory. A theory is a principle formed to explain the things already shown in data and has been widely accepted among the scientific community. Hypothesis testing allows an experimenter to assess the plausibility or credibility of a specific statement or hypothesis. For example, we try to prove the mean to be equal to some presumption value. For example, you can say mu is equal to 10. Then we denote the presumption value by, for example, mu 0, right? Then here we will do a hypothesis testing of a population mean. In this case, we have null hypothesis and alternative hypothesis. The null hypothesis for a population mean is the statement that designates possible values for the population mean, and we show h0 mu is equal to mu 0. The terminology hypothesis says that this statement will be examined with an appropriate data set. Always, a null hypothesis is associated with an alternative hypothesis that we show it by HA. This is the opposite of the null hypothesis. So we show HA that reject the null hypothesis, and it says mu is not equal to mu 0, right? Mu 0. So mu 0 is something that we found based on our sample. So in this case, mu 0 is the presumption value and mu is the population parameter. So for a two-sided set of hypothesis tests, H0 indicates mu is equal to mu 0. And in here, we want to check this one versus alternative hypothesis where mu is not equal to mu 0. This can be done for any specific value of mu. Then we have one-sided set of hypotheses that it says mu is less than or equal to mu 0 as the null hypothesis versus the alternative hypothesis that indicates mu is greater than mu 0. Let's see an example next. If you remember, we had an example in the previous lecture about the metal cylinders. Suppose we set the production line to make cylinders with a diameter of 50 millimeter. Regardless of the machine setting, there is always some variation in the cylinders produced. So it makes sense to conclude that the machine is calibrated correctly if the mean cylinder diameter mu is equal to the set amount. The two-sided hypotheses of interest are: null hypothesis says that mu is equal to 50, and on the other side, alternative hypothesis says mu is not equal to 50. So in this case, the null hypothesis states that the machine is calibrated correctly. So we can draw this if it is normally distributed like this, and mean is equal to like 50, right? Then we can say with the confidence of 95%, right? It means in here, we have 95%. So in this case, alpha is equal to 0.05, and alpha divided by 2, because it is two-sided, is equal to 0.25, right? So this area is the rejection area, right? So this area, we call it as rejection area. It means if the value falls in these two regions, we will reject the null hypothesis and we can conclude that alternative hypothesis is correct, and it means the machine is not calibrated correctly, right? So in here, we have like, for example, so this one here, 0.25, and this one, 0.25, right? Let's explore how we make that decision using p-values. We normally check the plausibility of a null hypothesis using p-values. P-value is a probability that takes the values between 0 and 1. So in some other references, you may see that they call it as observed level of significance. So the p-value measures how plausible the null hypothesis is given our sample data. So we check the plausibility of a null hypothesis using p-value, right? The smaller p-value, it means the less plausible is the null hypothesis. So we have a threshold. In some references, they consider it as 0.01. In some other references, it's less restrict, and they consider as 0.05 or 0.5, right? And 0.05 here and 0.5 here. So both are okay. Then when the p-value is less than 0.01 or 0.05, the null hypothesis H0 is not plausible statement. In this case, we will reject H0 and HA is correct. Alternative hypothesis is correct. Then if p-value is greater than 0.1, it means there is no substantial evidence that the H0 or null hypothesis is false. In this case, we have no strong inconsistency to reject the hypothesis, and therefore we accept the null hypothesis. However, this doesn't mean that the null hypothesis H0 has been proved to be true. Just we say we have no evidence to reject it, right? That's why we accept it. It doesn't mean it is true. And if p-value is between 0.01 and 0.1, it means the data analysis is inconclusive, and there is some fact that the null hypothesis is not possible, but the evidence is not overwhelming. So this one, we call it as intermediate p-values. So remember, we never prove the null hypothesis is true. We only assess the plausibility, right? A null hypothesis cannot be proved to be true. It can only be shown to be implausible. In the context of p-values, there are two common errors, type 1 error and type 2 error. A type 1 error is a false positive conclusion, while a type 2 error is a false negative conclusion. So we can call this as false positive, this one as false negative. Type 1 error, an error committed by rejecting the null hypothesis, but it is true. We call it as false error. We rejected the null hypothesis, but in fact it is true. On the other side, type 2 error is an error committed by accepting the null hypothesis, but it is wrong, right? We can call it as misdetection. For example, you decided to get tested for corona based on mild symptoms. There are two errors that could potentially occur. Type 1 error, the test result says you have coronavirus, but you don't have in real, right? And type 2 error, the test result says that you don't have a coronavirus, but in real, you have a coronavirus. So these are two errors. Then we have significance level here, that is the upper bound of the probability of type 1 error. Here is a clear way to understand errors using a table. So for example, this is our null hypothesis. If the null hypothesis is true and we fail to reject it, it means we have made a correct decision. So it is true and we didn't reject it, so it's okay, right? Then if the null hypothesis is true, but we rejected the null hypothesis, then we call it as type 1 error. In here, if the null hypothesis is false and we rejected the null hypothesis, then it's a correct decision. It's okay, right? And finally here, if we fail to reject a false null hypothesis, then this is called as type 2 error. So using this table, we can easily understand these kind of errors. Next, let's apply this to our cylinder example. Again, for the example of metal cylinder production, we want to see whether the machine can be shown to be calibrated correctly. So in this case, it is therefore appropriate to take the alternative hypothesis to be like H0 mu is equal to 50 and the alternative mu is not equal to 50. This mu is not equal to 50, this corresponds to a miscalibration. Then we go for p-values, right? If we get a small p-value, the null hypothesis is rejected. It means the machine is miscalibrated, right? The null hypothesis says the machine is correctly calibrated, right? But when we get small p-values, we reject the null hypothesis and it means the machine is not properly calibrated. But if we get a large p-value, the null hypothesis is accepted, and we can conclude that there is no evidence that the machine is calibrated incorrectly, right? So still, we cannot make sure that the machine has been correctly calibrated. We simply say we have no evidence to indicate that the machine was not calibrated correctly. Now, the main question is how to calculate the p-value. So we define the p-value as the probability of obtaining that our data set is okay or worse when the null hypothesis is true. In this definition, we need to take care of two things. One, this data set or worse, and then when the null hypothesis is true. Worst data set is one for which the null hypothesis is less plausible than it is for the actual observed data set. So here we consider a two-sided t-test, and here we have H0 as the null hypothesis where mu is equal to mu0 against the alternative hypothesis that states mu is not equal to mu0. We need to find out the disparity between the data set and the null hypothesis using a t-statistics. And we know that t-statistic is root square of n, where n is the number of sample size, x bar minus mu0 divided by standard deviation, and x bar is the sample mean. So if the x bar is equal to mu, then disparity is smallest and t value is equal to 0, right? It means this value is equal to 0. So p value, it means the probability that x is greater than or equal to absolute value of t, this area, plus probability of x less than or equal to minus absolute value of t, this area, right? So this is called as p-value, right? So in this figure, we can see the p-value for a two-sided test. Because it is symmetric, we can rewrite p-value as 2 multiply probability of x greater than or equal to absolute value of t. So once again, in order to calculate a p-value for a two-sided t-test, we use a t-statistic. This measures how far our sample mean is from the null hypothesis mean. We compare the t-value to a t-distribution to find the p-value. For a two-sided t-test, we define rejection and acceptance regions based on t-statistics. If the absolute value of t-statistic exceeds the critical area, then we reject the null hypothesis. If it is less than or equal to this value, we fail to reject null hypothesis. So let's see this concept visually. We have two datasets, dataset 1 and dataset 2, right? So as you can see here, there is more disparity between dataset 2 compared to dataset 1, right? It means this one is closer to mean and this one is far, right? It's a little bit wider. So for dataset 1, the distribution is narrower and it suggests less variability, or we can say larger sample size, and the critical region T is close to 0. However, for the dataset 2, the distribution is wider and it indicates greater variability or smaller sample size. Then in here, we have worse datasets. Worse means to have less affinity or dependency with the null hypothesis. So the blue color that you can see here, they represent the range of t-statistic for worse dataset compared to dataset 1. Because the t-statistic values of the second dataset here are less extreme, and this indicates that this outer region that you can see here are associated with smaller p-values and greater likelihood of rejection the null hypothesis. This implies that the data sets with t-statistics values falling in these outer regions are considered as worse. It means more likely to lead to reject the null hypothesis. So in terms of p-values, a worse data set would have a smaller p-value, as the t-statistic falling further into the rejection region increases the likelihood of rejection the null hypothesis. So which one is better? In the context of hypothesis test, the terminology of better data set typically refers to a data set that is less likely to lead to rejecting the null hypothesis. And this corresponds to a t-statistic closer to 0, right? Or you can say larger p-value. So in this image, dataset 1 has a narrower distribution around 0 compared to dataset 2. And this suggests dataset 1 is better because its t-statistics values are less likely to fall into the extreme regions compared to those of dataset 2. For the cases of one-sided t-test, if we consider hypothesis testing of h less than, so this the null hypothesis says that mu is less than or equal to mu0, and on the other side, the alternative hypothesis says mu is greater than mu0. Then the p-value for the one-side hypothesis testing is probability of x greater than t. And if we want to consider this hypothesis test, H0, the null hypothesis says mu is greater than or equal to mu 0 against the alternative hypothesis where mu is less than mu 0, then the p-value is probability of x less than t. In here, also x has a t distribution with n minus 1 degree of freedom, right? Where t is equal to root square of n x bar minus mu 0 divided by s, as we found already. Let's once again refer to example of metal cylinder production. We know that n is equal to 60 and the average is 49.99 and the standard deviation is 0.1334. So that mu 0 is equal to 50. We can find the t statistics as root square of n, sample mean, mu, standard deviation as this value, right? This is the t. Because it is a two-sided problem, then the p-value is equal to 2 multiplied probability of x greater than this value, right? Absolute value of this one, which is this value, right? So in here, we found that t is equal to this value and p-value is here, right? So if we want to find the p-value, we have degree of freedom 59, right? If we go to the table, then in here, just we add our t-value, right? So the t-value is, right? And degree of freedom is 59, then we can find 0.934, right? So the p-value is 0.934. Based on the image here, this one, right? So 0.934 divided by 2 is equal to 0.467, right? So 0.467 here and 0.467 here, right? And t is here. This p-value is 0.934 and this is greater than 0.1, right? So the null hypothesis is not rejected, right? We can say we failed to reject the null hypothesis, right? It means based on the information that we have, the sample data is equal to this one, right? We can define hypothesis test in terms of significance level or alpha. The hypothesis H0 test with the significance level or size alpha, right? So in this case, we reject the null hypothesis if p-value is smaller than alpha, right? And we accept the null hypothesis if p-value is larger than alpha. P-values are more informative than knowing whether a size alpha test accepts or rejects the null hypothesis. So in this figure, we can see a hypothesis test as size alpha. So we reject the hypothesis if p-value is less than alpha, and we accept the H0 null hypothesis if p-value is greater than alpha. We already know that for a two-sided t statistic, t is equal to root square of n, then x bar minus mu 0 divided by s, right? We want to make a decision to whether a size alpha two-sided hypothesis test reject or accept. We can do it by determining whether the absolute value of t falls in either rejection region or acceptance region, right? So the rejection region, it means the absolute value of t is greater than critical values, and the acceptance region, it means the absolute value of t is less than or equal to the critical values, right? We have a two-sided hypothesis test with size alpha. Then first we find the t statistics, the absolute value of t, and we go to the acceptance region. If the absolute value of t is less than or equal to critical values, then we accept it. Otherwise, we will go to the rejection area, and if absolute value of t is greater than critical value, then we reject the null hypothesis. Again, let's check our example of metal cylinder production. The data set of metal cylinder diameter gives a t statistics of absolute value of t is equal to 0.0836. So we have three possible values for alpha, 0.1, 0.05, and 0.01, 90, 95, 99, right? So based on the table, and in the previous lecture, we found that for this one is 1.671, 2001, and 2662, right? The critical point is 1.671 for a alpha of 0.1 hypothesis test. Then the critical point for this one is 2001 for a alpha of 0.05 hypothesis test. And the same here, 2.662 for alpha of 0.01 hypothesis test. The t statistic is smaller than each of these critical points. And so the hypothesis tests all accept the null hypothesis. The p-value is therefore known to be larger than 0.1, and we already found that p-value is 0.934. So now let's see the relationship between confidence intervals that we learned in the previous lecture and hypothesis test topic of today's lecture. Remember that we are looking to guess the population mean. We already found p-value and size of alpha. Now, if the p-value for the two-sided hypothesis test is larger than alpha, the value mu1 is contained within a 1 minus alpha level two-sided confidence interval. That is x bar minus this value and x bar plus this value, right? Critical point is y root square of n. So if mu is contained within the 1 minus alpha level confidence interval, then the hypothesis test with size alpha accept the null hypothesis. And if mu0 is not contained with 1 minus 1 alpha level confidence interval, then the hypothesis test with size alpha reject the null hypothesis. Then we can check the hypothesis. So let's see it visually. In this figure, we can see the relationship between hypothesis testing and confidence interval for a two-sided problem. We have x bar here, we have x bar plus this value and x bar minus this value as a critical point, right? We saw that the value of mu0 is contained within 1 minus alpha of two-sided confidence interval for mu if the p-value for this two-sided hypothesis is greater than alpha. So we have two cases here. One case is the outer area where p-value is less than alpha. And another case is this one, this inner area, this side, when p-value is greater than or equal to alpha, right? So in this case here, the plausibility is defined in terms of having p-value larger than alpha, right? And the outer side is for p-value less than alpha. So this is so these 2 points are rejection area, and this one is accepted area, right? The relationship between confidence interval, p-values, and significance levels are the same for one-sided problem as they are for two-sided problem. So one-sided inference on a population mean, it means mu is less than or equal to mu0 as the null hypothesis. A size of alpha test for the one-sided hypothesis, then h0 is less than or equal to mu0, and alternative says mu is greater than mu0. Then we accept if t is less than t alpha and minus 1, we accept it, and we go for rejection is t greater than or equal to this value, and we reject this one. These two figures, this one is for mu less than or equal to mu0, this one is for mu greater than or mu0. The rest is the same. The relationship between one-sided confidence intervals and one-sided hypothesis testing problem is like 1 minus alpha level, one-sided upper confidence is mu falls into x minus, and this side we don't have x plus this x bar plus this value, right? Plus infinity, right? So the mu falls into x minus this value and plus infinity. This interval consists of the values mu0 for which the hypothesis testing problem has a p-value larger than alpha. So two cases we have here, when p-value is less than alpha, this area, and when p-value is greater than alpha, this area, right? It means we accept it. Now we want to see the relationship between hypothesis testing and confidence interval for two-sided and one-sided problems. Let's consider three possible cases where null hypothesis says mu is equal to mu0 and alternative says is not equal to 0. Then it falls into this interval, x minus critical point s divided by n and x plus critical point s divided by n, right? So this is the critical point, standard deviation of sample size, right? Then the second case is where mu, so this is one-sided, right? The null hypothesis says mu is greater than or equal to mu0 and the other side is not equal. So minus infinity and the same, x bar plus this value. Then when the null hypothesis is mu less than or equal to mu0 and alternative hypothesis says mu is greater than mu0, then x bar minus this value and plus infinity. So this table summarizes the relationship between confidence level, p-value, and significance level, two-sided problem and one-sided problem, right? So we have some cases, p-value greater than 0.1, p-value between 0.05 and 0.1, p-value between 0.01 and 0.05, and p-value less than 0.01. If p-value is greater than 0.1, we accept the null hypothesis, right? If alpha is equal to 0.01, this is for 90%, this is for 95%, and this is for 99%, right? So in all cases, if the p-value is greater than 0.1, we accept the null hypothesis, right? And 1 minus alpha is equal to 90, and it contains mu0, and mu0 for all three cases. Then, if p-value is between 0.05 and 0.1, we reject the null hypothesis, but in this case, we accept the null hypothesis. And so the difference here is, this is 90%, right? And this is for 99%, right? And this is for 95%. So we accept the null hypothesis. Then this one for the 90%, it does not contain, but for 95% and 90%, it contains mu0. If the null value is between 0.01 and 0.05, we reject the null hypothesis. And the second case also we do the same, but in the case of 99%, we accept, and only for 99, it contains mu0. If it is less, then we reject for all possible cases. Now, let's see how to accept or reject the null hypothesis for one-sided inference on population mean when the null hypothesis say mu is less than or equal to mu0. A size of alpha test for a one-sided hypothesis, it means mu is the null hypothesis says mu is less than or equal to mu 0, and the alternative hypothesis says mu is greater than mu 0. So two cases, we can reject or accept the null hypothesis. If t is greater than t alpha n minus 1, then we reject the null hypothesis, right? And then if t is less than or equal to t alpha n minus 1, then we will accept the null hypothesis. It means we fail to reject it. So the other side in here, we consider that mu is less than or equal to mu 0. But other side is when the null hypothesis says mu is greater than mu 0, and the alternative hypothesis says mu is less than mu 0. Then if t is less than t alpha n minus 1, then we reject it. And if t is greater than or equal to t alpha n minus 1, then we will accept it. Now we want to study power levels. The power of hypothesis test is defined to be power is equal to 1 minus probability of type 2 error. So type 2 error when the null hypothesis is false, but we fail to reject it. So the larger power levels and shorter confidence intervals are both indication of an increase in the precise of experiments. Large values of power are good. Large power levels and shorter confidence intervals, it means we have an increase in the precision of an experiment. But we can choose only two quantities out of the sample size n, the significance level alpha, and the power of hypothesis test. Or similarly, only two out of the sample size n, the confidence level 1 minus alpha, and the length of a confidence interval. Once two of these quantities have been specified, the third is automatically determined. We already learned that we use z-test when we want to use an assumed or known standard deviation for the population, right? Instead of the s. It means we're going to use sigma. So z is equal to x minus mu 0 divided by sigma. This time we have sigma. It means population standard deviation. We don't use s anymore. So in here, in the case of t-test, we use t-test, s, and t alpha n minus 1. But in this case, we use z-test, and instead of s, we use sigma. And instead of this critical, we use z alpha. So for a two-sided hypothesis testing problem, the p-value is calculated as this one. P-value is equal to 2 multiplied probability of x greater than or equal to absolute value of z. In this case, we consider that x follows a normal distribution with mu and sigma squared. With the standard normal CDF cumulative distribution function of phi x, then we can write p-value as 2 multiply 1 minus phi z is equal to 2 multiply phi of minus z. The size alpha test rejects the null hypothesis or H0 if the t-statistics z falls into the rejection region, and rejection region is this one. Absolute value of z is greater than z alpha divided by 2. And on the other side, we accept the null hypothesis if the test statistics z falls into the acceptance region where x is less than or equal to z alpha by 2. Then the 1 minus alpha level two-sided confidence interval is mu falls into x bar minus and x bar plus this value z alpha, and this time we have sigma root square of n. The same, the only thing here is we don't have degree of freedom. So in here, no degree of freedom, no s. The rest is like t. So we have the same case for one-sided z-test. The p-value for one-sided hypothesis testing problem where the H0, the null hypothesis, says mu is less than or equal to mu 0. Based upon a data set of n observation with a sample mean of x bar and assumed known population standard deviation like sigma that we can see here, then p-value is 1 minus phi of z based on the table that we have. This testing procedure is called as one-sided z-test. A size alpha test rejects the null hypothesis where z is greater than z alpha, and it will accept it if z is less than or equal to z alpha. Then the confidence interval is one-sided, right? The upper side, the lower bound is x bar minus z alpha sigma standard deviation of population divided by root square of n. This consists of the values mu 0 for which this hypothesis testing problem has a p-value larger than alpha. That is the value mu 0 for which the size alpha hypothesis test accepts the null hypothesis. And we have the same case where this changes, right? So in this case, we have mu less than or equal to mu 0. In here, we have mu greater than or equal to mu 0. Then p-value is equal to phi z. So a size alpha test reject the null hypothesis where z is less than or equal to minus z, and accept the null hypothesis when z is greater than or equal to minus z alpha. Then the 1 minus alpha level one-sided confidence interval is x falls into the minus infinity up to upper bound, and this x bar minus z alpha sigma divided by root square of n. And this interval consists the value mu 0 where p-value is larger than alpha. All right, so let's move to Python coding. We want to try the data set of metal cylinder diameter. I will copy paste the data here. So this is our data. And for working with this data, we need to import NumPy. So then from Scipy, we need to import stats. And also for plotting, we're gonna import Matplotlib as plt. We need to consider some values for the hypothesis testing. The null hypothesis mean is mu underscore 0 for the null hypothesis is equal to 50, right? We want to check this one. And then we have alpha, the significance level as, for example, 0.05. Later, for the z-test, we're gonna assume some population standard deviation that is equal to, for example, 0.15, right? Now, we wanna calculate the sample statistics. So n is equal to length of our data, right? And we're gonna print it. N is equal to length of data, and we're gonna print this one, print f, and sample size is equal to n, right? So we have 60. Then we're gonna calculate the sample mean. Sample mean is equal to np dot mean of our data, and we're gonna print it, print f sample mean is equal to sample underscore mean, right? That is 49.99. Then we go for two decimal places, so 49.99. For the t-test, we need to find out the sample standard deviation. So sample underscore standard deviation is np.std. And in here, we're gonna pass our data, and also the degree of freedom is equal to 1, right? It means 60 minus 1 is 59, right? So we can print it, print sample std is equal to sample standard deviation with 4 decimal places, right? All right, now we want to calculate the t-statistic, right? Sample size is equal to 60, right? Sample mean is equal to 49.99, right? Sample standard deviation is equal to 0.113, right? And then mu 0 is equal to 50. Now we calculate the t-statistic. So t-statistic is equal to np dot sqrt of sample size multiply sample mean minus mu 0, and all divided by sample standard deviation, right? Then we can print it, print f t-statistic, and just we copy paste this one here, and we can print it. So it is minus 0.834, right? Then we're gonna find the p-value for two-sided t-test, right? So then here we can find the p-value. So p-value for two-sided t is equal to 2 multiply 1 minus, in here we use the CDF function, stats.t.cdf, and we will pass the absolute value of the NP, absolute value of t-statistic, and degree of freedom is equal to sample size minus 1, right? Then here we can print f, and then p-value of two-sided t-test is this one, 0.9338. And we can find the critical values as well. So t underscore critical underscore two-sided is equal to stats dot, this time ppf, right? ppf 1 minus cdf, ppf 1 minus alpha divided by 2, and degree of freedom is equal to n is equal to sample size minus 1. Then we can print it. So let's print the same here, print f, then this one is equal to 2001. Alpha here is considered as 0.05, right? Consider alpha as 0.05 for 95%. Then if you want to go for 99%, then here this one should be 0.01, right? So it will be 2.66. And if I change this one to alpha 2.1, then I can get 161, right? Based on that one that we got it. Now we're gonna try the decision, right? T decision is equal to whether to accept or reject, right? So T decision is equal to reject H0. It means reject the null hypothesis if p-value of two-sided is less than alpha, otherwise fail to reject the H0. So we fail to reject H0. Then also we can go for confidence intervals, right? So T confidence interval, lower bound is equal to sample mean based on the equation that we have, sample mean minus t underscore critical values for two-sided, critical value two-sided multiply sample standard deviation divided by n root square of n, right? And we can do, so we can print this one. So print C lower as 49.96, and we can do the same thing for the upper one. So this one here, sample mean minus, this time plus, right? And we can print it as 50.027. Now I'm gonna apply one-sided t-test. It means the alternative is mu greater than mu zero, right? So print, then here the t statistic will be the same as two-sided, right? T statistic is minus 0.08, right? Now here we calculate the p-value for one-sided, right? So p-value for one-sided t is equal to 1 minus CDF of t statistic and degree of freedom sample size minus 1, right? Then we can print it as it is 0.4669. Then we can print the critical t value. It means one-sided, right? So t underscore critical underscore one-sided is equal to t stat ppf 1 minus alpha sample size minus 1. Then it is 1.671, right? This is the t critical value for one-sided. So for simplicity, we can add alpha here. We can go for decision for one-sided, right? So t decision underscore one-sided is equal to, we reject the null hypothesis if p-value one-sided t is less than alpha, otherwise we reject it, so we fail to reject h0. And also here, we can go for 95% one-sided confidence interval lower bound because it's one-sided, right? So t underscore confidence interval one-sided lower is equal to sample mean minus t critical one-sided multiply sample size divided by root square of sample size, right? And it is 49.96. Then we can apply the z-test as well. So in order to find the z-statistic, we go for, based on the equation, sample mean minus mu divided by this time sigma, right? So we already consider one sigma for z, and sigma here is 0.15. This is the assumed population standard deviation, right? So this is the z-statistic, and here we can print it. Print f z-statistics, and it is equal. Print f z-statistics, and it is equal to minus 0.0744. Also, we can find out the p-value for two-sided z. P-value for two-sided z is equal to 2 multiply 1 minus CDF of absolute value of z, which is equal to 0.947. And also, we can print the critical z value, right? Z underscore critical underscore two-sided is equal to stats.norm ppf 1 minus alpha divided by 2, and we can print it as 1.96. Then here we can print the decision based on z-test. Z decision is equal to, we reject the null hypothesis if p-value is less than alpha, otherwise fail to reject, and the result is fail to reject, right? We can go and print the 95% confidence interval lower bound, right? So z underscore confidence interval lower bound is equal to sample mean minus z critical two-sided multiply sigma divided by root square. So which is 49.96. And in the same way, we can go for the upper bound. Upper is sample mean, this time plus z critical two-sided multiply sigma, and here we go for upper. Here it should be upper. So upper bound is 50.036. In the same way, we can do the one-sided z-test where the alternative is mu greater than mu zero, right? So we can print z-statistic is the same, right? As we already did it, 0.0744. Then we need to find the p-value for one-sided, right? P-value for one-sided is equal to 1 minus the stat.norm CDF of absolute value of the statistic, right? Then we can go for critical z value for one-sided. So z underscore critical one-sided is equal to stats dot stats.norm.ppf, and this time 1 minus alpha, which is equal to 1.6449. Then we can print the decision z underscore decision of one-sided is equal to reject if the p-value one-sided is less than alpha, otherwise accept. So we fail to reject x0. And also we can print the 95% one-sided confidence interval lower bound, right? So z underscore confidence interval one-sided lower is equal to sample mean minus z critical of one-sided multiplied sigma np root square of n, which is 49.96. Now we can go for plotting. So for plotting, I'm going to first plot histogram of cylinder diameters, plt.histogram. And in here, we're gonna pass data, beans, edge color is black, alpha is 0.7. And also here, we can add a line, right? So plt.axv line, axv line, then here sample mean, we print sample mean as well. So here you can see this is the histogram of data, and this red color is the sample mean. Then I'm going to plot a two-sided t-test. So in here, we need to generate some x value. So x is equal to np lean space from, for example, -4 to 4. Then here, the y values is equal to stats.t.pdf of x values, and also degree of freedom is equal to sample size -1, right? So these are the x values and p values. So then in here, we can plot the t-distribution. So plt.plot, and in here, we're gonna pass x values, t values, and t-distribution. Also here, we can add, like for example, df, which is equal to sample size -1, right? So if we add plt legend, so t distribution and tf is equal to sample size -1. It should be here. That's correct. Now we can add some vertical lines to show the t critical of two sided, right? So plt dot axv line, and in here we're gonna pass t underscore critical of two sided here, and color red and etc. It's okay. So this one, and next time just we gonna add the -1, right? Minus t of critical, and we don't need label here. Just the same. Correct. Next, we're gonna add some t statistic as well. So here plt.ax vertical line t statistics, and we show it in green. So this is a t statistic. And also we can fill these areas. So we have in PLT, we have fill underscore between to fill this rejection area. So x, t, and y underscore t, then where is equal to where x underscore t is greater than or equal to t underscore critical of two-sided, or the other side, right? There, or so this one, we should close it here, or this one plus this one less than or equal to, right? And here we can add like color is equal to gray, color is equal to gray, and alpha transparency this one, and we can print it at rejection area. So here, no, it's not right. Where xt greater than or equal to t critical two-sided, or xt less than or equal to minus this area. So you can see here that we have plotted, this is the green, the blue color is t distribution with degree of freedom 59. Then we have this red color, they show the critical values, and this green color is the t statistics, and this shaded area is the rejection areas, right? So this is how we can plot the t distribution. In the same way, we can do it for the z distribution. So we need to generate some values for z distribution, like -424, and in here we're gonna generate 1,000 variables. And then the y values is stat norm PDF of z values, right? Correct. Then here PLT plots xz and also yz, and then we label it as z distribution. That's correct. So this is the z distribution. So let's add the legend as well, plt.legend, right? So this is the z distribution. Now we're gonna add those vertical lines. So plt dot axv line z critical two-sided color is equal to red line style, and this one we can show it as, for example, z plus minus critical values. Then also we can add, so the next one is for, this one is for z critical two-sided minus z critical, and the same line style is okay. Then here we can also add the z statistics, and then we can fill x, y, where x is greater than z critical two-sided or less than minus this one, and then we can print the rejection area. So in this way, we can plot the z distribution, and we have these red colors are critical values, and this green one is z statistics, and these are the shaded areas are the rejection regions. Okay, that's it for our introduction to hypothesis testing. We have covered hypothesis, p-values, significance levels, and z-test using the metal cylinder example to bring it all together. Please practice this concept with your own data and join us next time for more statistical inference. Please feel free to ask me your questions by leaving a comment below this video lecture. Thank you and see you in the next lecture.